So then today we will start with this color correction. Okay, so we now understand a bit what is a color, and then we will try, we will start playing with colors. Okay, so this image has appeared a few times, and it conveys the idea that a color is a combination of three basic colors, and this basic is related to the basis in some vector space. We will see that today. Okay, so then let's start representing our vector space. So let's say that we have our RGB bases. So those are the basic vectors in this three-dimensional vector space. And then you have some particular color. So you have this color here. So you have a pixel, and that pixel here, it has these values. So what does it mean in that space? So it means that you have to take the red basic vector, that is this R hat, multiplied by 184, because the red channel was 184, and then take the green vector, multiply by 95, and the blue vector, and multiply by 2. And then that will give you another vector. This vector is the color of that pixel. So we can think of colors as vectors in some three-dimensional space. And then you can also encode them like this. This is the standard notation for vectors, right? Okay, but you know that this representation and this representation are equivalent. Okay, so what are these RGB? So those are the standard unit vectors in the three-dimensional space. Okay, so you would have, let's make them R. So the vector R would be 1, 0, 0. The vector G would be 0, 1, 0. And then the vector B would be 0, 0, 1. And then when you are saying, I have a pixel with a particular color, so let's say my color is RGB, this is my vector, then this is actually equal to R times R plus G times G plus B times B. So the ones with vectors are the unit vectors, and then the other ones are the coefficients in front of those vectors. Okay, so far this is very easy. Yeah, we have already discussed about this. So for instance, if I represent my numbers, my vectors with 8 bits unsigned integers, then for each one of the channels, I can go from 0 to 255. And then my space is discretized. So let me do it in 2 dimensions, because in 3 dimensions it's more difficult to draw. But if I have, let's make R and G, so let's say we have the R vector, this is the R direction, this is the G direction, and then our colors are discretized with 8 bits. Okay, so I can go 0, 1, 2, 3, 255, and the same for the other axis. So it would be 0, 1, 2, 3, 255. And then I cannot represent absolutely all colors in between. I can only represent these combinations. I can represent this one, this one, this one, also the ones on the axis. Okay, but my colors are distributed in a grid. You see? So I cannot represent a color. Let's use a different one. I cannot represent a different color that is here, in between points that I can store in my computer. So my space is actually discretized. So we are in some three-dimensional space, but we have a regular lattice in that space. If my RGB, so this is true, if RGB belongs to the set 0, 1, 2. If they are real numbers, I can represent absolutely anything in between, even negative numbers and so on. Okay. Okay, good. Then, if I have 3 vectors, or not three vectors, I have 3 components in a vector. How many possible colors? How large is my array, my lattice? It has 60 million entries. Okay, so I have it in this cube, that is within R cube. I have 60 million points, 60 million colors that I can represent with 8 bits. Okay, but then, so this would be my color cube, and then here are the red, green, and blue axes. And we already know that, for instance, red plus green is yellow. Okay, so that means that if I construct this vector, oh, sorry. So I have the vector yellow, that is my new point. My new point will be red plus green. So this is my yellow. And then I could have different kinds of yellow. So I could have yellow prime, that could be, I don't know, 254, 254, 0. Okay, so what I'm doing is moving along this axis. So I'm starting here at 0, 0. This is 255 to 55. Then I'm moving along this line. Okay, so this is 255 to 55, 254 to 54, and so on. So you have different intensities of yellow now. And we could, sorry. So we could have defined our bases in the color cube, like this one, the red, green, blue. But this is another axis. This is another basis. So I could define a different basis for my color cube, for my 3-dimensional space, and it is equally valid. So now we see the relationship between printing and displaying. So displaying in a screen is using this basis, while printing is using this basis. But there we can represent colors with both. As long as you have 3 vectors, you can represent 3 linearly independent vectors. You can represent any color in this cube. They don't even need to be orthogonal. Okay, so let's go to this idea again. So I want to reach, let me do it in 2D. Okay, so let me do it in 2D because it is easier to draw. Okay, so let's say that I have a vector u1, vector u2, and I want to represent this point here. Okay, so this point, let's make it like, so this point will be, I don't know, my point P, but there is some u1 times u1 plus u2 times u2. So the coordinates, if I want to express this in coordinates, would be u1, u2 in this basis. But let's say that I have a different basis. So now instead of the basis u1, u2, I have a different basis. So let's say I have this one, that are v1 and v2. So the same point now can be expressed differently. So it will be some other coordinate, v1, v2, and then the new coordinate will be this one. But they are pointing to the same point. Is that fine? Even these two bases, these two vectors didn't need to be orthogonal to each other. So orthogonal means that if I multiply v1 times v2, I get 0. So it is nice if they are orthogonal, because then these coordinates are very easy to calculate. But it is not needed. They could be whatever, so they could be like this, for instance. So they are not orthogonal. This would be my new v2. But they are also basis of this space. So I can reach any point in this space using this v1 and this v2. I use an extra coordinate. Okay, so let's make a new drawing. So I have this point, that is the one that I want to represent. But now my basis will be this one. So I want to express it as a function of 3 vectors. So now I have v1, v2, and v3. So now this point can be expressed in many ways. So yeah, let's try to do it. Okay, so this would be v1, some vector of v1. So v1, v2, v2. And in principle, let's say that v3, v3. Okay, so I just need two of them to get to this point. Any pair, okay? But I can use 3. So you can consider them to be like traveling instructions. So when you are saying I want to reach this point with u1, u2, what you are saying is, okay, so sorry. What they are saying is you have to travel in this direction u1, and then once you have reached that point, you have to travel in this direction u2. So as long as you have enough degrees of freedom, I don't want to get into the algebra of this, but it is very easy algebra. I don't want to get it. But as long as you have enough vectors that are linearly, they don't even need to be linearly independent. What you need, the exact construction is that, if you put all your vectors in a matrix, so you construct this matrix V that is made of your vectors. So those are your vectors in columns. What you need is that the rank of that matrix, so the exact condition is that the rank of V, you remember what is the rank of a matrix from algebra, right? So you need that the rank of the V is equal to the dimension of the space that you are the color space. So as long as you have a matrix whose rank is the dimension of the space, you can express with some traveling instructions, you can reach any point using any of the 3 vectors. The problem, not the problem, it is not the problem, it is actually an advantage, is that this representation is not unique. It is only unique for a basis. So if I have dimension 2 and I have 2 vectors that are linearly independent, then the instructions are unique. That is why we like bases. But if you have more vectors, you have more freedom, you have more ways to travel to reach a point. And now we understand this thing that we had yesterday. Okay, so we have R, G, B. This is a color cube. We have a new basis. The new basis is yellow. I don't know which one. cyan, I think, and magenta. Okay, so we understand now that this is another basis, but I don't need the basis. At least I need the basis. So I need at least 3 independent vectors. But I can add more. I can add more. So I can add an extra one that is black. So I can add an extra vector somewhere that is black. And now we understand, okay, so for displaying RGB basis is very good. For printing, I could have used CMY, but because CMY is more expensive, because coloring is more expensive, I can add an extra vector that is much cheaper. And then I can get any color using a combination of these 4 vectors. But now the combination is not unique, which is, in fact, actually it is good for you, because you can say, okay, I want to use as much of these traveling instructions as I want, because it is cheaper to travel along this line. So color codes are actually bases in this color cube space. Okay, let's continue with this idea. Okay, so this is the same. Yeah.
Adding another picture, which will be kind of redundant.
Yeah.
We're reduced the metric size, no?
The matrix size in which sense? This V, you mean?
Yes.
You are increasing, no? If you add more vectors, the matrix is increasing.
I mean the maximum or the last vector of the matrix.
The last?
Vector of the matrix. Say, for example, if we have black, which means 255 for every color,
That is 0.
that's 0.
0.
If we have black, that means that we don't need the 0, 0, 0 from the other colors.
Yeah.
Directly 1.
Actually, it is a bit more complicated, because when you, this is a color cube. Why centering the origin there? So I could have centered the origin. Let's draw the color cube. So this is the same representation as this one. So now this origin is this one. Why putting the origin there and not in here, for instance? I could put the origin there. This is black. Okay, so black is here. So now, but if I put my origin in here, that is white. This is white, because it is 255, 255 in all directions. Now the black vector goes in this direction. Let's make it. You see? So the black vector doesn't need to be 0, 0, 0. Depends on what is your origin. Okay. So when you have a display, the origin is here. 0, 0, 0 is doing nothing, I get black. If I have a paper that is white, 0, 0, 0 is white. So my origin in my color cube is somewhere else. And now the black vector goes in the opposite direction. Okay, so then, this idea that I can reach any color by following different instructions, traveling instructions, is well represented here. So for instance here, I want to reach this point, then you have to travel R0 in this direction, and then you have to travel G0 in this direction, and then you have to travel B0 in this direction, and then you have reached the point. But if you want to reach the same point, now following a different basis, then whatever you have to travel is different. So there will be some different traveling instructions. So you have to travel C0 in this direction, and then you have to travel Y0 in this direction, and then M0. And now you have reached the same point. So let's try to make some changes in our color. So let's say that we have this image and we want to make it more green or more blue or more red or whatever other transformation in colors. Okay, so let's say that I have this this image. These are the standard histograms of the different channels, the RGB channels. And now I apply a gamma transformation to the red channel. Okay, so gamma transformation, we already know what it is. So we apply a gamma equal to transformation to the red channel, only to the red channel. So now the red channel is compressed. So this area is increasing the contrast. This area is reducing the contrast. So that is why we have these spikes. And now we have the image becomes a bit more red. Okay. So in this somehow we are moving in that direction. Okay. Now let's have the original again, and now we apply a gamma equals 0.5. So now we are shifting the image towards the low region of red, and now it becomes less red. So less red. This is not more blue. It is more blue or more cyan because it is less red, because we are reducing the red. Then gamma equal 2 in the green, so it becomes more green. Or gamma equals 0.5 in the green, so it becomes less green. And then more blue, less blue. So when you move in the direction of more blue, you are moving in this direction. When you are moving in the less blue direction, you are moving in the opposite direction. But the opposite direction is yellow. So it is not that you are making it more yellow. It is more yellow because it is less blue. But in your RGB basis, you cannot be more yellow somehow. Okay, so then this RGB color space is not the only one that we can have. So we can have any other representation. So the color cube is fixed. So all those are all the colors that we can represent. But the RGB basis is not the only one. We can construct any other kind of representation of a color. So for instance, we can have the RGB that we are already familiar, but we can also construct something that is decompose into something that is luminance, that is basically how many photons are arriving, and what are the wavelengths of those photons. So those are called chroma, chrominance, hue and saturation. So they have different names because they have different bases and different ways to construct those two components. But the idea is always the same. How many photons? What is the color of those photons? What are the wavelengths of those photons? And we have already said that the brain mostly works in this luminance and in colors, two channels of colors, but on the RGB. The RGB is more related to the eye. But then in the information transfer to the brain, there is this transformation into intensity and chrominance. Yeah, this is interesting. This was the first attempt to try to organize the colors in some meaningful way. And it was done by Maxwell, the same guy of the Maxwell's equations. So he tried to organize the colors in some way, and he was the first one saying, okay, we might have the colors might be a vector that is somehow a composition of different 3 locations in a space, in the color space. And then a particular color would be a combination of these 3 corners. But forget about this. We have a much better representation now. This much better representation will be something like this. We will expand this idea much further. So how do I transfer from an RGB representation of a color to something that is kind of intensity and chrominance? So this is the one we will study. This is called intensity and then saturation and hue. So it is value actually, value, hue and saturation. Okay, so let's say that I have this point color here. And in this triangle, I can tell you how to reach that point if I tell you the following. So you start traveling from the middle of the triangle. And then I tell you kind of polar coordinates, how far you have to go. So that is the saturation. So if you don't have to travel much, then the saturation is 0. So you would stay at the origin of the triangle. And if the saturation is large, then you would have to travel a lot. And then the hue is in which direction you have to travel. So I will tell you the angle in which you have to travel. So it is actually in this triangle.
¿Está aquí Eva?
¿Quién?
Eva.
¿Está Eva?
Eva de profesora.
No.
¿Me ha hecho una espera aquí? Vale, no,
Pues a lo mejor te has equivocado de aula, a lo mejor te he
no,
dicho
no,
otra.
no, 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 desde este vídeo, vamos.
No. Bueno, no sé.
Vamos.
Okay, so this is simply a polar coordinate in this triangle. Okay, good. So yeah, we will expand that much further. Yeah.
This triangular representation, I expected, for example, the yellow to be the same area, visually same than the blue. I mean, the opposites of the blue should be something with the same extension.
Yeah, yeah. And the thing is that all colors, we need a cube to represent all colors. And we are just representing a triangle here, so we cannot represent all colors. And that is the mismatch that you see between this representation of what you have in mind probably. How did we come to this triangle? By cutting the color cube. So you have a color cube. Now the origin is here. So that is the 0, 0 point. This would be black, this would be white. And then let's say that you have a color. Okay, so you have the color, or we will think of all colors such that R plus D plus B is equal C. Okay, what is that? That is the equation of a plane in the color cube. Okay, if this is my origin and this is my vector space, this is the equation of a plane. And it is the equation of a plane. We remember this from your geometry classes. But if I have R plus G plus B equals C, I can express this as RGB, that are my color points, times 1, 1, 1 equals C. And that is the equation. That is the equation of the plane R, G, B. It is a plane such that the normal of that plane is 1, 1, 1. And it cuts this axis at a distance C. I'm very bad at drawing, but I think you get the idea. Okay, so you cut at points C in each one of the axes, and the perpendicular to the plane is 1, 1, 1. 1. Okay, that is what we have represented now. Only that the origin is there. So this is the cut of all points, all colors, such that they fulfill this equation. And there are three interesting points that are these ones. These are where the plane cuts the basis axis. And for instance, if you put C equal to 55, so if you put C equal to 55, you are cutting the axis exactly at the corner. That is a triangle. And that is why you don't see yellow, because that triangle doesn't contain yellow. Yellow is somewhere else. Yellow is here. Okay, then let's look at some of those cuts. Okay, so let's look at. We can see the intersection of this plane with this other plane, with the triangle, or the plane containing the triangle. Okay, so what is this plane? So what is the characteristic of this plane? So here we have blue axis, we have the this is the red axis, and this is the green axis. So what is the characteristic of this plane? So this plane here, this face of the cube, is the equation of that plane.
The values of red color.
No. This green equals 0. So that plane so now we have two planes. One is this, let's make it red. And the other one is the intersection of this, intersection the green equals 0. And then if green equals 0, what is the intersection of these two? It is a line. You may remember this, if you have two planes, the intersection is a line. Which line? Red plus B. Red plus B equals C, and G equals C. So it is all the points such that red is whatever, green is 0, and then the blue is C minus R. How many free parameters do you have here? Just one, the R. We have R as free parameter, something that I can change. And then, since I have only 1 degree of freedom, what I have is a line. How many degrees of freedom do I have here? So let's plot all these points. So all these points, they are of the form. Okay, so R can be whatever, G can be whatever, but then B is restricted to be R minus G. So I have 2 degrees of freedom. So that is why those are a plane. Those are in a plane. What about this one? What are all the points that belong to this plane? So R can be whatever, G has to be 0, and B can be whatever. So again, I have 2 degrees of freedom, and that is why those are also a plane. Okay, so now, here what we have is this intersection between the plane R plus B plus G equals C, with C equal to 55, just for representing, and then the G equals 0 phase. And then this phase is this one. You can imagine, you can extract this phase, and if you extract it, what you get. And this line here is the intersection between the two planes. And this line here, all the points in this line, they have this shape. Okay, so they have this shape here. So R can be whatever, then 0 and then C minus R. C in this example was 255. So you would have 0, 0 to 55, or 1, 0 to 54, or on the other extreme, 255, 0, 0. So this point would be the 0, 0 to 55, so red is equal 0. And then you are traveling all the way to red 255, and then the other two has to be 0. And then what is this V? This V is the value. That is what we had at the beginning in one of the first lessons. We were computing the value of a color. So we were computing the value. We were saying the value of a color is R plus D plus B divided by 3. But R plus D plus B is C. So this is C divided by 3. Within that plane. So all the points within the same plane, they have the same value. So that plane is defined by, so those planes are defined by all the colors that have the same value. So they have the same, the value, you may remember it was kind of a way of summarizing the 3 channels into just one intensity. So all these colors, they have the same value. They have kind of the same intensity. What if I increase C? So I make C larger. So now the value will be larger. Another intersection is not anymore a triangle, but now the intersection is an hexagon with the color cube. And this happens for all the C's between 255 and 510. So before 255, for all the C's that are smaller than 255, this intersection is a triangle. Then between 255 and 510, what I have the intersection is an hexagon. And then if I keep increasing C, this is just one of the cards, for instance here. Let's look at this card again. So this intersection between the G equals 0 plane and the R plus G plus B equals C. So now we have this line. So that line is here. This is our line of intersection. The origin is here. Okay, so then, if I keep, this is another card. So now this is the plane. This is with the plane G equal 255. So instead of looking at G equals 0, instead of looking at G equals 0, I can look at G equal 255. That is another plane. And now this would be the phase that I have to extract. And that is what I get. Now the origin is here. Okay. And then we can look at different cards with different planes. So we have here the plane. So this is the plane. Red equals 0, red equals 255, B equals 0, B equals 255. But those are lines. All those intersections have to be lines because those are the intersections of two planes. Okay, so yeah, now let's look from the color cube facing, so the origin is behind the hexagon. So here is the whole color cube somehow rendered, and these are the triangles that we are constructing. Okay, so what happens? We don't have a slide for that, but what happens? So we have been discussing those intersections as a function of C. So for C smaller than 255, it is a triangle. For C between 255 and 510, it is an hexagon. But you keep increasing C, so you keep moving this plane farther and farther away. Then at some moment, the intersections are triangles again. You see? Okay, so now we will explore this HSV representation. Oh. Okay, so we are 2 minutes outside our interval, so let's make a break and we continue. So, any questions so far? No? Okay, so then let's study this HSV color representation. This is another way of representing colors. It is just one, so that you get an idea of how these RGB representations can be transferred to something that is decomposed into intensity plus 2 color channels. Okay, so let's say that we have the RGB space, and we have a point in that RGB space, and this will be R0, G0, P0. Now, we take the plane that contains that point, and that has normal 1, 1, 1. So this is the plane, okay? R plus G plus V has to be equal to this. So this plane contains this point. Now, we will translate this R of G0 V0 into V0. So this is HSV, so HSV. Okay, so what are those HSV? Okay, so V is the module of this vector. But this vector is made in this way. Okay, so you take the color point that you want to translate, you compute the value, and now you travel along this direction, this value. This is the 1, 1, 1 direction. So you travel in this direction, the value of the color. So this is nothing more than what we were doing with the triangles and intersections. So you are computing the value, and then you are going from the origin to the plane. So now we are at the triangle. Okay, what else? So now we have V. Let's construct S. Okay, so S will be, you take the color you are trying to represent, you take the point in the triangle of the hexagon, you take the point in the triangle that contains your color, and that is at the middle of that triangle, and then you compute this difference. And S is the module, is the length of that vector. So now we have S and V, and we're missing H. Okay, so what is H? So H is the angle between this point lies in the red axis. So what we are taking is, this is the point at which the plane intersects the R axis. So this is all points in this plane, they have this value, this sum of them. So this C. Now we are traveling C in the direction of R. So we are going all the way through this axis and reaching that point. Now I compute the vector that goes from here to V. So I'm computing this vector. So it is the vector that goes from V to R. You see, you start at V and you finish in this point. So you have this vector. And you have the S vector. So the S vector was P naught minus V naught. So it was this color minus this one. So it is the vector that starts here and finishes there. So you're measuring the angle. So H is the angle between this vector here and the vector S. So yeah, we'll go a bit more step by step again. And now you get the flavor. So what we are doing is, somehow you had a vector. And with the help of these planes and this axis and so on, you measure, you define different vectors, you define what are the lengths of those vectors, what are the angles between those vectors. And then you're encoding the same information, but now as a function of something different. It is the same information. We will see this again in more detail.
Can we go back to the H is zero movement? Is it
The H is
or sweep into the horizontal one?
H is within the plane. So it is within the intersection plane. It is how much you have to travel. We will see this later, but A, S and H, they are polar coordinates within the plane. But I think it will become more clear in the next slides. Okay, so this is what this value V naught is. Okay, so now the origin is here. Okay, so we have the plane that contains our color point. Okay, good. So this is at the point that we want to express, and this is the plane that contains that point. Now, so this is the A. So this is our color that we want to represent. Okay, good. Then, this is the same. There is a line, the 111 line. So the 111 line, let us think of that line. So the color along the 111 line will have, let's say, some constant C, and then 111. That is, we have the same color in the three axes, in the three bands. And we already know that colors that have the same value in the three bands, they are gray values. So they go from 0, 0, 0, that is black, to 255 to 55 to 55, that is white. Then we have all the gray colors in between. So if we plot those lines, those colors in the color cube, they are this line. So all colors in the 111 line, they are these colors. So we have this diagonal, and this diagonal will intersect the plane at some point. Okay, so this point where it intersects is V. It is this vector V naught that we defined at the beginning. This V naught is that point where the diagonal intersects the triangle. Okay, now, what is S? S is the vector that goes from that point of intersection to the color that we want to represent. And that vector has to be in the plane. It's fully contained in the plane. Because the origin is in the plane, the point we are going to is in the plane, if we go in a straight line, this straight line is fully contained in the plane. Okay, so now we have the vector v. The vector v is the one from the origin to the gray point in this plane. And this is also something interesting. All these plane intersections, all these triangles, hexagons, they all contain a point that is gray. That is the point v. Okay, so we have the vector v, we have the vector s going from the gray point in that plane, and there is a single gray point in the plane to the color point that we want to represent, that is s. And now you go from v to the intersection of the plane with the r vector, with the r basis, okay, to the most red point in that plane, in that intersection. So you have this vector. So h is the angle between going from v to the red and the s vector. And this vector is also contained in the plane. You see, this going from the gray to the most red point in the plane. This vector is fully contained in the plane again. So we could do this analysis of the angles of h and s just contained in the intersection plane. Okay, so now we have another representation of the same idea. Okay, so now, yeah.
Which information does the S vector bring to us actually?
Say it again.
Which information does the S vector bring to us?
It is. Okay, so let's say that I want to reach that point. Okay, that is the color I want to reach. Then HSV, they're telling us how to reach that point, but now with different instructions. So V tells you have to go this far. Once you have gone this far from the origin, you will find a plane, a triangle or an hexagon containing a plane. Okay, that plane will have a direction. So now we need some coordinates within that plane. Okay, so we need something that is fixed. So what is fixed is the direction from the gray point to the most red point. So this axis is fixed. So for every plane, for every one of these triangles, this axis is well defined. Okay, so now, once you have found that axis, you have to travel counterclockwise with the distance s. So s is giving you the distance, and h is giving you the angle that you have to travel. Good. So now, all this algebra, I think it becomes more meaningful. So it looks complicated, but okay, it is simply a way of formalizing what we are describing. Okay, so you have to travel along, away from the origin, you have to travel v, then you will find a triangle or an hexagon. In that triangle or hexagon, there is a very well-defined direction, that is the point going from the gray to the most red point in that plane. This is this thing. And then I will tell you how much you have to travel, which is the angle, and at which distance. So these two are polar coordinates within the plane. And this is giving you the plane. You see? Okay, so yeah, more representations around these ideas, but now they are more kind of redundant with what we know. Okay, so we have the RGB bases. These are the sides of the color cube. Okay, so those G equals 0, B equals 0, R equals 0 planes. And now we are cutting at different values. So this is B equal 10, then B equal 21, B equal 32, 50, whatever. You have the values there. So up to here, the intersections are triangles. Then we start intersecting into hexagons. These are our hexagons. Then this is still an hexagon, They're not regular hexagons, okay? And then at some point, the intersections become triangles again. And at some the same, but now with different representation. Okay, so now in the more okay, we understand how to compute these things, but now tell me some instructions I can encode into a program. So you are given this point, R naught, G naught, V naught. Then you will compute V naught as 1/3 of C, and C is the sum of the three. Now, you will construct this vector V naught, that is V0, V0, V0. And now you construct S naught, that is this subtraction. And then S naught, so this is a vector, this is the module of that vector, the length of that vector. So you simply take the length of that, so this is the length of this. Okay, so these are things that you can very easily compute. So you are given a point, then you compute C, you compute V naught, you compute this thing. See? Then I have to construct the most red point in my plane. Which is the most red point in my plane? So C we already have, that is R plus G plus V. So the most red point in this plane is this C00. And this is the gray point. So this vector here, this vector is always well defined. So given any color, this vector is unique. And this one is the one that we had from the previous slide. And then I simply have to compute the angle between the two. So it is the arc cosine of this dot product divided by the length of the two. Sorry. Okay. So these are the instructions that you could follow to make the transformation. Okay, so now something relatively simple. Okay, so what is the maximum saturation that I can have? So the maximum saturation I can have is reached when the maximum red is this one, 255.00, and then the color I'm representing is this one. And if you compute what is the maximum saturation, it is this 208. Okay, so you explore all possible saturations that I can have for all the colors in the color cube. And the maximum is obtained for this for the white. Okay, and the saturation of white is 208. Okay, good. Then instead of encoding this length of S, what we keep in the computer is the length of S divided by 208. Now it is a number between 0 and 1. So the saturation is a number between 0 and 1 that tells you how far you are from a gray color. Yeah, so those are small details. So what happens if this is 0 divided by 0, but we don't care about these small details. So in an implementation, in a true implementation, you have to take care of small cases or just kind of particular cases. But we want to focus mostly on what is the meaning of those transformations. So somehow our brain is not computing all these things of cosines and angles and all that, but somehow it is translating the RGB information from the eye into something that is more similar to this thing. So it has an intensity, so it has more or less kind of how many photons you have, that is the value. And then two chrominance components. So here we have seen one, that is this saturation and hue, but it could be whatever. Okay? So if you look at different color encodings, you have many different ones with different chrominance definitions. So we have defined, for instance, this direction to the most red point in the plane. Why the most red? You could have defined any other thing that is well defined. Okay, so those are the differences between those. Okay, so just for completeness, let's say that we want to go back. So I want to go from an HSV representation to an RGB code. Okay, so let's think of a coordinate axis that is defined on my plane. So I have my plane, my triangle. The origin is at the gray point. So this is the only gray point in this triangle. And then I will have a vector v that goes out. So this is perpendicular to the plane. And then I have x that goes from the gray point to the most red point. And then y has to be orthogonal to these two. So if this is 0, 0, 1, when I define this to be 1, 0, 0, then y has to be 0, 1, 0, because it has to be orthogonal to the other two. You can construct y as the cross product between v and x. Okay. Okay, good. So now, within that plane, what we have is are polar coordinates. So I know that in this coordinate system, my color can be expressed in this way. So I have to travel in this direction by an amount given by hue. The radial component is s. So I know that within the plane, in this coordinate system, my color is s cosine the hue times this vector, and then s sine the hue times this vector. This is simply for coordinates. And then I am within the plane, so I don't have to go out. I have 0 times v. But this is in the coordinate system of the x, y, v coordinate system. But the vector I want is not in the x, y, v coordinate system. I want this vector, but now in the RGB coordinate system. So I have to translate this coordinate, that is simply polar coordinates within the plane, into coordinates of the kind of universal RGB coordinate system. Okay, so let's do that. Okay, so you may remember that if I want to translate, okay, let me do it first here. So What do we know so far? Okay, so my color code in the HSV coordinate system, it is like this. So it is S, I don't remember if it is cosine or sine, I think it is cosine. Yeah. So it is S cosine of the hue times X plus S sine of H Y plus 0 V. We are using this for vectors. Okay, but this is in the in the X, Y, V coordinate system. Okay, what if I want to express this in the RGB? So in the RGB coordinate system, what I have to do is, it is the same, but now this X has to be expressed in the new coordinate system. I have to express this vector in this system plus S sine of H, and then I have to express this vector in the other system. And then 0 times whatever, but 0 times whatever is 0, so we don't care. So, sorry, this is not a good notation. Notation should have the RGB outside. Okay, so I have to express X and Y in the RGB coordinate system. Okay, good, let's do that. So that is what we are doing here. So, okay, so what about this vector? So this vector, okay, so this is the same idea. The coordinates in the RGB coordinate system are different from the coordinates in the X, Y, V coordinate system. Okay, so now I need to find this representation of the vectors X that are the basis, X, Y, V, that are the basis in my plane. I have to find those expressions in the RGB coordinate system. Okay, so this is the same equation I wrote in the whiteboard. Okay, so let's look for that. Yeah, this is a bit more algebra, but let's forget about this for the moment. We'll come back to that later. Okay, so now, what is V in the RGB coordinate system? So V goes in the 1, 1, 1 direction. So V is 1, 1, 1, and if we want to make it a unit vector, so the length is 1, we have to divide by the normal 1, 1, 1. The normal 1, 1, 1 is 1 over square root of 3, that is equal to that. Okay? Now, so V is very easy to express. What about X and Y? Okay, so let's look at X. X, it is perpendicular to V and has equal G and B components. So the most wet point, so let's come to here. So I have V. Okay, so I have V in the RGB. I think it is more easy to understand like this. Now, what about X? Okay, so X in the RGB. So we are trying to represent. We are trying to represent this vector. Okay, so this X that goes from the gray to the most wet point. Okay, so it is a vector such that it has to be perpendicular to V and needs to have equal G and B components. So it will have same, so it can have whatever red value, and then the green value, and the blue has to be the same as the green. And now it has to be perpendicular to this one. Okay, so it has to be such that 1/3 times R plus 1/3 times G plus 1/3 times G again is equal to 0. So that will give you, we can remove all this. So you have that G has to be minus R divided by 2. So all those vectors, all the vectors of the form R minus R half minus R half fulfill this condition. So the G and B components are equal, and they are perpendicular to this one. Among all those vectors, there is only one that has unit length. So that is fixing the R. Okay, so now the condition is R squared plus R divided by 2 squared plus R divided by 2 squared has to be 1. Now you solve for R. So there is only one that has a unit length. And that one is this one. This is the only vector that is perpendicular to B, has equal G and B components, and has unit length. Okay, so it was hard, but not so difficult to get V and X. What about Y? Y is very easy, because Y has to be the cross product between B and X. So simply you multiply and you get this one. Okay, so now we have X, Y, and B in the RGB space. So all we have to do is to take. Now we have solved for this. We have solved for this thing here, this thing there. And we didn't write because it was multiplied by 0. But if we want to be complete, we would also need that B. Okay, and now we have it. Now comes the matrix. Okay. This in general, this is some coordinate, let's say X. This is some coordinate Y. This is some coordinate B. So in general, if you have an X, Y, B coordinate, how do I translate it into an RGB coordinate? So I can express this the following way. I can express this as, this will be a matrix that has X, RGB, and then Y, RGB, and then B, RGB, multiplied by X, Y, and these are column vectors. Okay, so these are column vectors. And this whole matrix, so this whole matrix, I can call it A. So now summarizing. The RG, so make it like this. So the P coordinates in the RGB system is some matrix A times the XIV, but the XIV is the coordinates in the XYV. And now you recognize something of algebra that probably you remind. That is, if I wanted to change a point from some coordinates from one coordinate system to another coordinate system, but I have to multiply it by a matrix. And this matrix is the expression of this coordinate system expressed as a function of the other coordinate system. So it is the x, y, v expressed now in the RGB coordinate system. And the transformation looks weird. So this matrix, the matrix is presented somewhere. So the transformation looks very weird, but it is very simple. It is simply all this reasoning of V. V is a 1, 1, 1 vector, unit length vector in the 1, 1, 1 direction. Then x goes from the gray value to the most red value. And then y has to be perpendicular. So now, following all this reasoning, so all these angles and all that, now it is very easy. It's very easy. This is all you have to do. So you have an HSV vector. You can translate into well, not HSV because it has to be HSV. Remind that those x and y, they are related to the HSV through this relationship. Okay, so x and y, they are not h and s. So they are related by polar transformation. So you take HS, you compute XI, and then use this transformation to go from XIV to RGB. But you can also do in the other direction. So if I want to go from RGB to to HSV, I can invert this one. So I can say P at XYV is A minus 1 and then the RTB. So, and this matrix is invertible, so I can take this coordinate, translate into XID, and then once I am in the plane, I simply compute the polar coordinates. So now colors have nothing more than vectors, and all the algebra that you can do with vectors, those are meaningful operations with colors. All this is now some nice representations. So things we can do, for instance, let's say we consider the plane R plus D plus B equal something. Okay, it gives us this hexagon, and then we can decompose the hexagon into the RGB components. Yeah, you can do beautiful things. What about hue, saturation, and value? So this plane, all colors in that plane has the same values, has the same intensity. What about the saturation? Saturation tells you how far you are from the gray point. The gray point is at the middle. In this color plane, there is only one point that is gray, that is there in the middle. The saturation is how far you are from the middle. And the hue tells you which is the way, how far you are from the most red point. The most red point is up here. So how far you are from this line, but now in angle. Okay, so how do you have to travel in that signal? So our brain somehow works more like this. So how much intensity you are receiving, and then somehow the colors they are encoded in some way, okay? But not RGB. Now we can put colors. So now we have, let's say, an image. Now I can do operations on the saturation and on some other space. So I have the RGB. We have done these gamma transformations in the R and D and B channels, but I could do also transformations in the HSB. So, for instance, let's say the saturation is traveling farther in this direction, so making them more saturated or less saturated. So less saturated means more gray, and more saturated means more colorful. Okay, so I can increase the saturation by 1.5. So I multiply the saturation by 1.5. I can decrease the saturation. I make it less colorful, more gray. And I can do funny operations on the hue. So the hue is an angle. So if you give me a color, here, the hue is the angle between this line and that color. Okay, so now I can do operations with angles. So I can shift that angle by, for instance, let's say 60 degrees. So I turn all the colors 60 degrees. So let's look at this. So for instance, we have red somewhere. So I have red. And if I turn the red point that is here, if I turn it 60 degrees, it will become yellow. And a yellow point, a yellow color, will become green. And the green color will become, I don't know, cyan and so on. So now my colors are shifted. Red, by a turn of 60 degrees, red will become yellow, yellow will become green, and so on. So now, if I apply it to that, so now the image looks like that, and then I can make a turn of 120 degrees, 180 degrees. These were the complementary colors that we were seeing yesterday. Those are the colors that have exactly the opposite response from the cones in our eye. So this would be the negative, and 240, 30, and 360. And this is the how the hue. So we can represent the histograms of the red, green, and blue, but I can also make a histogram along the hue. So I take the saturation and I compute. So now these are angles. Okay, so this is 0, 60, 120, and so on. So I can make a histogram along angles, and I can see what are the predominant colors. So I have a lot of red, I have a lot of blue, and as I turn my colors by adding 60 degrees, everything shifts to the right. 20, 180, and so on. So, any question? Now, I think the main change today is that now we see colors in a different way. So, colors are vectors, and whatever you can do with vectors, you are changing your colors. And you can be very creative about the way you express your vectors, the way you treat your vectors. And those will be nice operational colors. Some of them will be useful, some of them will be garbage. But now you see colors in a different way, I think. No question? No? Okay, so I prefer to start this tomorrow on next day because it is the whole block again. So, okay, so let's leave it here.
Thank you.